Good morning, grade 9. Welcome to our first online lesson for science. I thought it would be good for us to go over some of the things that we were learning before we left a few weeks ago. And we're going to start with all the things that were really important for electric circuits. So we're going to begin with Ohm's law. And Ohm's law is the mathematical relationship between voltage, current, and resistance. So if V is equal to I times R. I'll also have you note of that very handy triangle, which if I set up V, I, and R as such, we get an easy way to quickly find what the mathematical relationship is for the other variables if we're a little shaky at rearranging and doing that algebra. So if I want to know V, I already know it's I times R, but I cover up V and I get I next to R, and that means multiplication. If I would like to know I, for example, I cover up I get V over R, so V divided by R. And if I want to know R, that would be V divided by I. I'll also note that it was important to remember all the different ways we can talk about voltage, current, and resistance. So, for example, voltage measured in volts with a unit symbol of V. Current measured in amps with a unit symbol of A. And finally, resistance measured in ohms with the symbol omega. So it looks like that. So the next thing we're going to look at is we're going to apply this to the circuit we have right here, which is a series circuit with one resistor and one LED. So we have a voltage source tied to a resistor and an LED. And this is a series circuit. The voltage is around 2.5 volts, and the resistance is 330 ohms. We may wish to calculate the current running through the circuit. So I want to know the current. This is equal to V divided by R. So it's equal to 2.5 divided by 330. And that gives us, we can put our calculator for this, 2.5 divided by 330 is 0.0075. That repeats, so we'll just say 0.0075 repeated amps. And so roughly this current is 7.6 milliamps. So that's the application of Ohm's law within this particular circuit. And it would be useful to actually be able to measure that. So I'll bring the circuit over here, and we're going to measure the current running through the circuit. And so for that, I have a voltmeter. or I guess this is a voltmeter and an ammeter, so it is multifunction, so we call it a multimeter. And I can measure a few things in this circuit, but I want to measure the current that I just calculated for. And in order to do that, I actually have to disconnect the circuit. And then reconnect it by making the circuit, the electricity pass through the multimeter. So our light bulb lights up again once this is actually connected, and we get 7.54. So that's pretty close to our 7.6 number that we calculated for. And so being very close is actually very good. And one of the reasons being is that all the wires, even the LED, has a little bit of resistance. So that's going to kind of alter this number we get in the end here. So nothing's quite perfect, but we were quite close, which is good. The next thing that we're going to look at, I'm going to reconnect this circuit here, is a parallel circuit. And this was a circuit which had multiple different pathways. So we're going to take our circuit that we have here, and we're going to create another pathway. So normally it looks a little bit like this. And resistor, LED, and we'll add another pathway with a capacitor. So we'll have a resistor, an LED, and a capacitor. We'll say LED. And this is our voltage source. So we'll also do that here on our circuit that we have. And what's good to note is that our electricity, as it comes out of the battery, the electrons, have two different options here once they get to that junction point. They can go through the capacitor, or they can go through the resistor and the LED. And they will do both. And so we have two pathways here. And so I want to implement that capacitor in our circuit. So here's what our capacitor looks like. It has a negative strip here, and that tells you kind of how to hook it up. And I'll put the negative end into the wire coming from the negative power rail. And we now have a parallel circuit. It didn't really change all that much. We still have an LED that is lit up, but now we have a capacitor in there, and that will serve a very particular function, which if we actually disconnect the battery, our LED will very simply fade away. We'll see that one more time. We have negative end, positive end. And if we disconnect the battery, the LED, which we see there is on, will slowly fade away to darkness. So that's kind of the practical application of a capacitor. You see these a lot in electronics because, like our LED, lots of electronics are susceptible to really sudden shifts in the power supply. So disconnecting that is a very quick change for the power supply, and electronics can sometimes be broken through this. And so capacitors are implemented to very gradually change the power supply if it happens to be disconnected. This was one type of parallel circuit, and a parallel circuit, a different type of parallel circuit, just to highlight that there's lots of different ways to draw these, could be implemented as so. And this could be the example of a parallel circuit. So we have two pathways here into an LED, and then we also have a switch. We could also implement another pathway here. The options are really endless for when we try and implement a parallel circuit. And so what would be very useful to note here is that our voltage source is tied into a couple different lights, and we have some switches. So the resistors are there simply to make sure that the LEDs don't burn out. The switches, however, have some different functions. You'll notice that this switch is kind of like a master switch. It controls all of the pathways going back into the battery, or actually the way I drew it, coming out of the battery. So that means we'll have to switch a few things up here. We'd actually have to reverse the direction of the LEDs. So kind of like this. That would be this LED in here. And then this one would have to go that way. Because LEDs are directional. So that would kind of, this master switch controls everything. So if that were off, both LEDs would be off. And if this switch here were off, just this LED would be off, but electricity would still be able to flow through that LED. And so parallel circuits are often very practical for the lights that are wired in your house. That's everything for today.